Quick question. What is 726 divided by 3? I'll give you 3 seconds. Okay, the answer is 242. If you couldn't solve this in 3 seconds, that's okay. I'll give you another chance. Here we go. What is 726 divided by 3? See how this time you already knew the answer without having to make any calculations? You simply reuse the information that was already available in your short-term memory. This is how caching works in computing. When you're browsing Facebook and you go into somebody's profile, the browser requests for the profile owner's display picture, and the server responds back with the image file, which is then rendered onto your browser. The browser, however, keeps track of this information in something called cache memory. This way, when you visit the same profile again, the browser doesn't have to request the server anymore. It just needs to find it from its cache memory. But you spend a lot of time browsing Facebook, which means you've been to several profiles, and each of these profiles' display pictures are getting added to your browser's cache. But there's a limit to the amount of information that can be saved to your browser's cache. Once we reach this cache memory limit, what do you do with the next display picture when you visit a new profile? There's no extra space to save this in our cache, so the only way to make this work is to delete an existing picture from the cache. But we need to be careful about which one will be deleted. It makes sense to delete only the least recently accessed display picture from the cache. This is a famous caching algorithm called LRU Cache, which is short for least recently used cache. This is also a commonly asked interview problem. In this video, I'm going to show you how to solve the Leetcode problem number 146, LRU Cache. This is one of my favorite Leetcode problems. Before you can tackle this, you'll need to know a couple of data structures. First is HashMaps. Whenever you have a set of data where each of the data can be represented in key value pairs, consider HashMaps. Each element in a HashMap has a key and a value. Imagine the key as an employee ID and value as an object with the corresponding employee details. Now imagine if you have 1,000 employees in your HashMap. If you ask the HashMap about employee details of employee ID 502, HashMap goes, here you go. If you put the same 1,000 employee details into an array and ask for employee ID 502, array needs to search, is this 502? No. Is this 502? No. And that takes time. So in short, HashMaps have faster lookup time. The second thing you need to know is a data structure called doubly linked lists. Here you have a list of objects. We'll call them nodes for now. So we have a bunch of nodes. Each node has a data. In our case, we need a key and a value. Each node also has a reference to the next node and the previous node. In a doubly linked list, you only have access to the head node, which is the beginning of the list, and tail node, which is the ending node. But that's only need to traverse the entire list, because you can use the next pointers in each node starting from the head to reach the tail, and similarly you can use the previous pointers to go from tail to head. For this problem, we are going to keep the head and the tail nodes as dummy nodes, which means we're not going to set a value for them. The main reason we use doubly linked list for the LRU cache problem is because it is time efficient to remove or add elements to a linked list. We can remove a node by updating next and previous pointers of its adjacent nodes. You can add to the front of a linked list by updating pointers of the head node and the next of the head node. So let's keep these two data structures in mind when we're solving this problem. This problem expects you to define the behavior of a new data structure LRU cache. Implement the LRU cache class. Initialize the LRU cache with a positive capacity. Implement get method that takes in a key and returns its corresponding value. If the key is not present, return -1. So let's use a hash map of integer key and integer value for this. This is kind of like when you browse Facebook and you go into a profile you already visited. The browser gets you the image file, which is the profile picture. Update the value of the key if the key exists. Otherwise, add the key value pair to the cache. If the number of keys exceed the capacity, evict the least recently used key. This is exactly the same scenario that I mentioned before about browser keeping profile pictures in its cache. If we reach the cache memory limit, we'll have to remove the least used item from the cache. So the problem is basically asking us to keep track of the order in which each item in the cache was recently used. If we use a doubly linked list of keys in your hash map, we can keep that order. Whenever a get is called, we check if it already exists in the cache. We can do that by checking if the key exists in our hash map. If it exists, we remove that node and add it to the front of the list. If it doesn't exist, then we just return -1. Pretty simple, right? Now for the put method, firstly we'll check if the key already exists in the map. If it does exist, we should update the value, remove the node from the list, and add the removed node to the front of the list. The front of the list is the most recently used item. If the key does not exist in the map, it means we're adding a new element to the cache. Here we need to be a bit careful. If the cache is at its limit already, we cannot simply add a new element. We need to delete the least recently used item from the cache. The item that we should remove is the tail of our doubly linked list. We use that key to remove from the hash map, and then we remove it from the doubly linked list as well. Once we have removed this, we can add the new key value pair into our hash map and create a new node based on the key and add it to the front of the list, because now this is the most recently used cache. I really hope that you enjoyed this video. If you did, please consider subscribing. I'm also looking forward to your comments on this video. See you soon.